Here, I just to mention that last time I'm missing a p here, and then I highlighted here, and then it will result into the p square, and then that will complete what we get here. So the p is coming from the chain rule, which is the coefficient for our exponential of t. So that's just one detail from last time. Okay, and also the notes that is published on the Canvas also have these details. So just in case if you needed any correction from last time, I also published this version on the Canvas. Okay, so yeah, today's material, and we'll also cover some information that are related to the homework. Okay. Yes. So maybe let's just do another examples regarding moment-generating function as a warm-up here. Okay. So for x that follow a Poisson distribution, so this is the distribution that we encounter during in week 0, where we use this as an example to calculate the expectation and the second moment. So in this particular examples is that we are going to calculate its moment-generating function and then use the moment-generating function to calculate the first moment and the second moment. So again, for the support is all the natural number including 0, and also for the parameter lambda greater than 0. So to construct the moment-generating function, m for random variable x, and then it's a function of t, we can start from the definition of the moment-generating function, which is the expected value e raised to the power of tx. And then Poisson is a discrete random variables. So we can do summation for all possible x, which is the support, and then e raised to the power of tx, and then multiply by the probability mass function for the Poisson distribution. And also from our first lecture, it is lambda raised to the power of x, and then e raised to the power of negative x, and then x factorial. Okay, so now we're just going to simplify this equation and then resulting in our moment-generating function. So any thoughts on how we can simplify this? So maybe first we can bring whatever is not related to our summation or x here outside the summation. So in our case is the e raised to the power of negative lambda. As it does not involving x, everything this can serve as a coefficient. So that is the first step. And then let's work on the remaining term inside the summation. And we can group the things in the following way, or particularly the numerator. So we have the lambda multiplied by e raised to the power of t, and then altogether raised to the power of x, and then x factorial. So now by looking at this summation, does that reminds you of anything that we can simplify that? Also from the first lecture. So what we did in the first lecture is that, or what we saw is that e of x, or exp x, can be written as an infinite summation for, let's use index n, from 0 to infinity. And x raised to the power of n, and then n factorial. So what we can do is that we mimic this particular expression and then rewrite this part also as exponential terms. So we can write this term as the following. So first of all, we have our coefficient e raised to the power of negative lambda, and then we can write this summation as e raised to the power of x, except that the x in our case is the terms in the parentheses. So we have e raised to the power of lambda e to the power of t. So that will be the by expressing this infinite sum, into a single term. And then we can further group them together as e raised to the power of lambda and then et minus 1. And this is the moment generating function for the Poisson distribution. Okay. Any question or comments up to this point? So we're just reusing what we did in the first lecture and then express or calculating the moment generating function. Also, from the first lecture, we calculated the e of x is equal to lambda, and also the variance of x for a Poisson random variable is also lambda. So in this case, or in this examples, we're going to use moment generating function to calculate these two terms, just like what we did in the previous lecture. Okay, so for this examples, we need to take the derivative with respect to t, right? Because moment generating function is a function of t. So we need to take the first order derivative and then set it equal to 0. Okay, so essentially we just need to take a derivative for this expression. So what we have is that itself and then multiply by something coming from the chain rule. And the chain rule is referring to the derivative of the exponent here. So for this part, when we take the derivative with respect to t, we have another copy of lambda and then another copy of et. Does that make sense? And then for the second step, evaluate it at t equals 0. Okay, so for the first term here, or this part that I underlined, when we plug in t equals 0, what does that equal to? E to the what? Why is that? Yes. 1, right? Yes, okay. Good, thanks. Yeah. So 1 multiplied by the lambda. And then what about the second term when we plug in t equals 0? 1, right? Okay, good. Yeah. And then we have another lambda. So this is the first moment. So if you still recall from the first lecture, we did the whole blackboard to calculate this lambda here. But actually using moment generating function, you just need one line, and then you can get your answer. Yeah. So again, when you want to calculate the moments, it really depends on whichever you find it easier, which method that you want to use. So in this case, maybe using moment generating function is easier. But for binomial distribution, like what we showed last time, it can be very complicated with a product rule. So moment generating function may not be a good option. So it's up to your preference when you want to calculate the moments. Yeah. Okay, so now we can talk about the second moments, which is just a second order derivative and set t equals 0. So here we have our first order derivative. So now we just need to take another derivative for this expression with respect to t. And as you can see that there are two terms that involving t from now. You also need to use the product rule here. Okay, so let's take the derivative and let's take the derivative first. So maybe we can work on this term here first. So the derivative of this is essentially just the whole thing, which is just the first order derivative. So we can just copy that down here. T minus 1 multiplied by lambda and then et. So this is also coming from the second term. But don't forget, this is a product rule. So we also need to take the derivative of this, multiply. I think we are missing, yeah. So this is the derivative of the part that I, So this part is the derivative of the part that I underlined. Do you agree with that? And then we need to multiply by this part. So we have another lambda and then e raised to the power of t. And then for the product rule, we also need to add another part, which is the derivative of this part multiplied by this part. Okay. So essentially is that lambda multiplied by e raised to the power of t, and then multiply by, let me clean up a little bit notation here. Multiply. Okay, so that is the result for taking another derivative for this expression, particularly using the product rule. Okay, do you agree with that, or particularly this result? Okay, then for the next step, evaluate the whole expression at t equal to 0. So let's see what we get here. So if we plug in 0, this part we already evaluated, which is one copy of lambda. And then we have another copy of lambda from here, and then this also reduced to 1. And then for the second term, when we plug in t equals 0, we have one copy of lambda, and then one copy of 1, and then multiply by, let's see, also a 1, right? So in the end, for the second order derivative, after we set t equals 0, we have a lambda squared plus a lambda. So that is the result for the second moment. And lastly, we want to calculate the variance. So variance of x, again, using the formula, is the expected value for x squared minus the square of the first moment. So we have a lambda squared plus a lambda minus the square of the first moment, which is the square of a copy of lambda. And in the end, we have the variance equal to lambda. So yeah, so what we did here, or in this example, is that we first calculating the momentary function from the definition. So that's a definition. And then we arrive at this particular expression. And then we use the first order derivative and the second order derivative to calculate the first moment and the second moment when we set t equals 0. And then we verified the first moment is equal to lambda. This is also the second moment, and this is the variance. So you will get exactly the same thing as what you see in the first lecture. Yeah. All we did is just using another approach to calculate those. Any question regarding this? It's just a verification from the first lecture for those terms, and then using the method that we did from last time, or on Tuesday. Any question or comments? Okay, if not, then let's introduce, or let's talk about another new distribution, and this is starting to relate it to the homework. Yeah, so what we want to talk today is that the gamma distribution with parameter alpha and beta. So this is a distribution with two parameters. So previously we have seen that the exponential distribution have a parameter of lambda. The Poisson distribution have a parameter of lambda, and also some other distribution. But in this particular distribution, there are two lambda that we need to worry about. Yeah. Anyone know what is the support for a gamma distribution? which is all the non-negative real numbers, so x greater than 0. And what about the constraint for the parameter? They should all be greater than 0. Okay, so after we mention or specify these details, and now we can proceed to the probability density function for this random variables. So this is a continuous random variables. So we use f of x to denote its density, probability density function. And then it has the following expression. So you have the random variable x raised to the power of alpha minus 1, and then multiply by e raised to the power of negative x over beta. So this whole thing is on the exponent. And then over a gamma function, which I will talk about later, which you write as a gamma with a number. In our case, this is the alpha, which is one of the parameter. And then multiply by beta raised to the power of alpha. And this is the expression for the probability density function. Yeah. So sometimes when you Google or looking at the Wikipedia, they have some other expressions, but they essentially have the same form, except that whether you take the inverse of the alpha or the beta. But just to make sure that if you see something different, it's probably just people sometimes change some of their notation, but essentially they have the same formulation, just in case. Maybe later in the other parts of the lectures or in this course, I will rewrite this formulation into a different notation, but essentially they're the same thing. Okay. Just want to put it out there. Okay, that's that. And also related to the homework, which is the kernel function. So essentially the kernel function is just referring to the numerator, which is just the x alpha minus 1 and then e raised to the x over beta. So the kernel function is just referring to this part. And also for probability density function, sometimes you will see people call or mention something called normalizing constant. So the normalizing constant is a particular constant for a distribution that make the probability mass, when you sum everything together, it will end up to 1. Because not all the function, when you sum from negative infinity to positive infinity, will get you a 1, which is not a probability density function. It's just a function, density function. But when you integrate, if you wanted to integrate from everything and then equal to 1, you need to divide your kernel function, for example, in this case, by this part, which we call it the normalizing constant. And then after you integrate that from the real number or from all of your support, you will get an area under the curve equal to 1. So that is the purpose for the normalizing constant. Okay, so I would like to spend this part to emphasize that when you integrate the kernel function for the support for this random variable, you will end up with the normalizing constant. So that you divide it by the normalizing constant, when you integrate the whole thing again, you will end up with an area under the curve equal to 1. Let's just verify what I just said. Okay, so what we want is that we want to integrate from x equal to 0 to positive infinity, and then only for the kernel function. And then dx. Okay, so now when we're looking at this expression, we notice that there's an x here, there's also an x here. Any thoughts on how we evaluate or simplify this integral here? I think one thing we can do is also from the technique from last lecture is that we can make the change of variables. So what we can do here is that we set another random variable called y, and then set it equal to x over beta. So then we have x is equal to beta y from our construction. And then we can call dx equal to beta dy. So this is what we do for the change of variables. Okay. And then with this construction, we can start to put things inside the integral, or to replace the terms in the integral to make it simplify. Okay. So for x, let's first write down the upper bound and lower bound. And then let's replace the x here with the beta y that come from our construction. So we have beta multiplied by y raised to the power of alpha minus 1. And then for the second part, we have the exponential of negative y. And then for the dx, we need to replace by beta multiplied by dy. So now we essentially change the integral with respect to x to with respect to y. Also, let me ask again, what is the support for this new integral here when we're with respect to y? What is the lower bound here? Now we change it to y. So what you can do, again, is that you can plug in the upper bound, lower bound into our construction. So our lower bound is x equal to 0, plug it in, lower bound become y equal to 0, and y equal to infinity. Okay, let's see what else we can do to simplify this. So the integral is with respect to y. So one thing we can do is to move whatever not related to y outside the integral. So what we have is that beta raised to the power of alpha minus 1, and also this beta here. So essentially we have beta raised to the power of alpha outside, right? And then we have y raised to the power of alpha minus 1, and then e raised to the power of negative y here. And then dy. Okay, so now I just want to mention that this particular thing is the definition for a gamma function. So here I would just like to make the distinguish between this notation here. So when you describe a random variable or a probability distribution, you write this notation, the gamma notation. So if you want to do it in LaTeX, this is a uppercase gamma and then backward slash, something like that. Yeah. So this is referring to the gamma distribution. So you usually put the parameter inside this parenthesis here. And here, for the denominator, this thing here is referring to a gamma function. And the gamma function has this particular definition. So this is a gamma of alpha. So this particular integral is referring to the gamma function. And this alpha can take like real values. And then for some special case, for example, when alpha is a natural number, is like an integer, then the gamma function is essentially the alpha minus 1 factorial. You can also using this integral to get this result here. But this is just a special case for this integral. And let me put down one more property for this gamma function. and then I will pause for question. So another thing is that when you have a gamma function, alpha plus 1, this can be rewrite as alpha multiplied by gamma function alpha. Okay, so these are two special case for the gamma function that we will use later. So I'll pause here to see if there's any question. Okay. Then this integral here is just essentially the definition for a gamma function, and this part reduced to the gamma function evaluated when you input alpha, and then you have a copy of beta raised to the power of alpha. And this is essentially what you see when you see the definition for a gamma distribution, which is just this denominator. And then, so what we show is that when you integrate the kernel function, you will end up with the normalizing constant, and which already serves its purpose. When you divide it by that constant, and then when you integrate again, so for example, when you integrate this particular expression from 0 to infinity, then you will end up with 1. So that the area under the curve for a probability density function always equal to 1. Okay, so yep, that is just some definition and then some comments regarding this new probability density function that we talk about here. Any question regarding this particular distribution? Okay, if not, then we will now calculating the moments for this particular distribution. And what I will be showing is that the expected value for x raised to the power of k, so the kth moment essentially. So in the homework, let's see. Yes, here, for exercise 3, you are essentially asking for e of x and the variance of x. So what you need to do is just to calculate e of x, the expected value for x, and the expected value for x squared. So what I'm going to show here is for a general case, for a general k. So in the homework, all you need to do is just following the same procedure, except that you plug in k equal to 1 and 2, and then you will get your answer for exercise 3. Okay. But here, I'm just going to show a more general case for an arbitrary k. Does that make sense? Okay. So here, let's use the definition for expectation. So again, what you can think of this is that this is g of x is equal to x raised to the power of k, and then multiplied by f of x. So we're going to use that kind of a definition to evaluate this expectation. Okay, so first let's write down x raised to the power of k. And then we have the probability density function. Okay, so now all we need to do is just to simplify this and then also resulting in a closed form, and that will serve as the moments for an arbitrary kth moment. So one thing we can do, as what we have did every time, is that we bring whatever is not related to the random variable of interest, because we are evaluating with respect to x. So whatever not related to x, we can bring it outside to the integral. So what we have is that the gamma function and then the beta raised to the power of alpha, and then 1 over that. Because nothing involving x, so we can bring it outside as a coefficient or as a constant. And then let's combine the terms inside the integral. So what we have is x raised to the power of alpha plus 1 copy of k from here, and then minus a 1. And then for e raised to the power of x over beta dx. And also, this is given in the hint for your exercise 3, is that you multiply and divide it by something, the same thing. It does not change the quantity, but it will help you to evaluate the integral. So this is also given in the hint for exercise 3. So what it means is that we are going to multiply a 1 here. You multiply and divide it by something, essentially it is equal to you multiply by 1. And to complete that is that 1 over the gamma function of alpha. And then what we want to multiply is the following. So we want to multiply another copy of gamma function for alpha plus k, and then beta raised to the power of alpha plus k. So now we multiply by a particular quantity here, and we also want to divide it by that so that it does not change this whole quantity here. That is what it means by multiply by 1. So we can divide it by that inside the integral. So we have x for alpha plus k minus a 1, and then e for x over beta. And then here, we divide it by what we multiply in the beginning. So that is in the denominator. And then dx. So this does not alter the quantity, right? Do you agree with that? So we essentially just multiply by 1, and we construct this 1 by this expression. You multiply by this gamma function and beta, and then you divide it by the same thing. So you should not change the quantity. But the reason is why we want to do this. And the reason is that when we look into the integral here, this is essentially another gamma distribution. And this random variable x now following a new gamma distribution with alpha plus k and beta by construction. And then, as I mentioned earlier, when you integrate this whole probability density function, so this thing should give you a 1 as well, because you are evaluating the integral from its own support. So in the end, you are left with the following expression. Alpha plus k, and then the original normalizing constant from the random variable x. And now we can further simplify this expression. So maybe you can first talk about the beta. So on the numerator, we have beta raised to the power of alpha plus k. And for the denominator, we have the beta raised to the power of alpha. So what we left is just a copy of beta raised to the power of k. So that is the beta part. And what about the, let's see. Okay, so one thing in your homework is that you only want to evaluate the first moment and the second moment. So you will have a k equal to 1 or 2. And for that case, you can use this property here. So this is essentially like alpha plus k, where k equal to 1. So in the homework, you are asked to calculate when k equal to 1, k equal to 2. So for that case, you can use this property here to simplify your expression in your homework. But because here we are talking about an arbitrary k, so we don't know that the number for that k, so I'm going to leave it as a fraction for now. Does that make sense for everyone? Or okay, so so now let me just plug in k equal to 1 and k equal to 2 to get e of x and then e of x squared. And these are just the solution for your homework 3. But the homework 3 is more, the homework exercise 3. But essentially the exercise 3 is asking for the process, the same process here. Yeah. So let me provide you the solution so that you can also verify. So for k that equal to 1, okay, so let me just complete just to emphasize again, this is the moments, the kth moments for a gamma random variable. Okay, just in case you forget what we're doing here. Okay, so now we set k equal to 1, we should have e of x. So the first moment. And then let's bring k equal to 1 into this expression. So we have beta raised to the power of 1, and then alpha plus 1. And then you will have a gamma function of 1. So now we can use the property that I mentioned earlier here, which is this one. Alpha plus 1 is equal to alpha multiplied by gamma function of alpha. So we will have beta alpha gamma of alpha gamma of alpha, and this reduced to alpha beta. So the product of the parameter for your gamma distribution. And this should be your solution for the exercise 3. So you can use this to verify whether you have the procedure correct or not. Okay, then for the k equal to 2 case, we will have the expected value for x raised to the power of 2. And now let's plug in k equal to 2 in this expression. We will have beta raised to the power of 2, gamma function of alpha plus 2, and then gamma of alpha. Okay, so we can again apply the same property here. So we will have one copy of alpha multiplied by alpha plus 1 over gamma of alpha. And then we apply the property again to alpha plus 1 to get beta squared alpha, sorry, 1 second. Sorry, this should not be alpha. This should be alpha plus 1. Okay, so let me elaborate a little bit here. So what we want to do is that apply the formula for alpha plus 1 equal to alpha multiplied by gamma of alpha. But what we have here is gamma function of alpha plus 2. So you can consider this as a gamma function of alpha plus 1 plus another 1. And then you regard this as, let's say, alpha star. So what you have is that a gamma of alpha star plus 1. And this is equal to alpha star of gamma function of alpha star when you apply the property. And then now you bring back the alpha star with alpha plus 1. And then gamma function of alpha plus 1. And that is what we have for the numerator here. So make sure when you apply the properties, make sure you know what is your alpha here, or your alpha star. Yeah. Yeah. But yeah, now let's coming back to this particular expression. The denominator is gamma alpha, but what we have is one copy of gamma function of alpha plus 1. So we need to apply again to cancel out the denominator. So we have a alpha plus 1 multiplied by alpha multiplied by gamma of alpha divided by that. So in the end, for the second moment, you will have a alpha plus 1 multiplied by alpha multiplied by beta squared. And that will give you alpha squared beta squared plus alpha beta squared. And that should be your second moments. And you can also verify this when you are working on your homework. And let me just finish the variance and then I will pause for a question. So the variance, this is also asked in the homework. So for the variance is that the second moment minus the square of the first moment. So all we need to do is just plug in the k equal to 2 case. So alpha beta square and then minus the square of the first moment. And the square of the first moment is alpha beta here. So we minus alpha beta square. And then you end up with alpha multiplied by beta square. And that is your variance. So these two terms are the solution to your exercise 3. But the homework is asking for this particular procedure. So make sure you show the work here and then use the k equal to 1 and 2 specifically when you're developing exercise 3. And that is what the reader will be looking for, the grader. Yeah. But your answer will be equal to these two. Okay, so I will pause here to see if there's any question. So there's no question, comments? Okay. Then let's see. Oh, okay. So yeah, what we did is that using the integration, divided and multiplied by something, and then integral equal to 1. And we also show why we want that equal to 1. And also I provided this thing. So everything I just mentioned is also given in this hint here. And then let's see what else I can talk about. Okay, so later I will talk about some other things related to exercise 6 and 7. But first of all, just to complete our discussion for the gamma distribution, I want to also calculating the moment generating function for a gamma distribution. So that will be what we're going to do next. So let me do this as an example. So what we want is the moment generating function for the gamma distribution. And this is equal to the expected value for e raised to the power of tx. And then again, I'm just copying down the definition for the expected value, etx, and then x raised to the power of alpha minus 1 dx. So this is just a definition for the expected value. Okay, so now by looking at this term here, anyone has any thought on how to simplify this? So now we are seeing three different x's here. There are locations with 3x here. Any thoughts on how to simplify this? Okay, so when usually working with the momentary function, the first thing you want to do is actually to group the tx with especially this exponential of tx with something already in from the density. So what I meant is, let's rewrite the integral in the following way. So x raised to the power of alpha minus 1, and let's rewrite the e, the exponential, in the following way. So negative x multiply by 1 over beta minus a t. Do you agree with that in the exponent? So what I'm doing is that e of a multiplied by e of b is equal to e of a plus b. So I'm going to use this as my a and this as my b, and then I'm grouping them together. So I bring the negative sign outside. They all share an x, so I bring it outside the parenthesis. You have a one copy of 1 over beta minus a y, because there's a minus sign here. Is that okay for everyone? Yeah. So what I did is just I grouped this term and this term from the numerator together. And then we have the same denominator. And then dx. Okay, so next, also using some technique as what we did in the first example, is that we want to make the change of variables. So now we are going to set y when we introduce another random variable as x multiply by 1 over beta minus a t. So this is by construction. We introduce y and then set it equal to that. And then what we want is that we also want to have another expression for this dx. So now let's write x in terms of y. So 1 over beta minus a t. Let's take the inverse here. Multiply by y. So that dx is equal to 1 over beta minus t inverse dy. Okay, so now we have a y by construction, and also we have an expression for dx. And all we can do is that replacing all the components from the original problem. Okay. So I will leave the upper bound, the lower bound as blank for now, and then later I will ask you again what is the upper bound, lower bound. So here for x, we have 1 over beta minus t. So raised to the power of negative 1. but we also have a power of alpha minus 1 here. So what we get is a, let's see. Okay, so maybe let me write it in this way. So I use the y. Okay, maybe I'm not going to jump too much. So we have this just to make it. So all I did here is just to replace the x by bringing this inside the x. Yeah, and then alpha minus 1. And then for the exponential, we have e raised to the power of negative y. And then a gamma function of alpha, and then beta raised to the power of alpha. And then for the dx, we have 1 over beta minus t inverse, and then dy. Okay. So now let me circle back. What is the upper bound and lower bound here when you express this as in terms of y? So here is x equal to 0, x equal to infinity. What is the upper bound, lower bound here for y? 0. And then what about upper bound? Yes. Okay, thanks. And let's see what else we can do to simplify this. So what we can do is to bring whatever not related to the random variable or not affected by this integrate operation outside the integral. So let's see what are irrelevant to that. So for example, this is irrelevant, so we can bring that outside the integral. Minus 1. And what else is irrelevant? We have a constant here, so we can also make that outside the integral. And don't forget there's a minus 1 here, and then a alpha minus 1 here. So you have a alpha, a negative alpha minus 1 here. Do you agree with that? So I'm just bringing the constant, not related to y, outside the integral. And now work on the integral for 0 to infinity. So what we left, or the remaining parts, is the y alpha minus 1, and then e raised to the power of negative y, and then the normalizing constant. Okay, does this equal to 1 or not? Think about it. So if we write it, simplify up to this point, does this integral equal to 1 or not? So it does not yet equal to 1. But our goal is that we want to make the integral equal to 1 to disappear. The reason is that the density function, the density function is that you need to have the random variable y divided by the beta. So what we are going to do is that we divide it by 1. Okay, maybe let me start another line then, not to confuse you. Okay, so what we have is up to this point, but this is not yet equal to 1, and then we are going to further modify this integral in the following way. 1 over beta minus a t inverse Okay, so maybe at this stage, let me also group them together. So you have a negative alpha minus a 1, and then you also have one copy of minus 1. So you have 1 over beta minus t. So this is negative alpha plus 1 minus a 1. You only have a negative alpha. Is that okay for the exponent? Negative alpha plus 1 minus a 1. So you only have one copy of, so you only raise the power of negative alpha here. Okay. And we are also going to bring out the denominator beta alpha from here, because this is first of all not related to y, and also does not make this integral equal to 1. So let's bring the things that is not helpful outside the integral. Then let's finish the integral, and then we also introduce some more things here. So now I'm going to write the exponent as y over 1. It does not change the integral, right? And then we have a gamma function of alpha. But now we also need to complete whatever here to make it equal to 1. So what can we do here? So what should we put it here? Sorry? We want to complete the density function for the gamma distribution. So the density function has a beta raised to the power of alpha. So one thing you can consider is that when we introduce the 1 here, we are essentially setting the new beta, let's call it beta, I'll just call it beta, beta star equal to 1. So that you will have 1 raised to the power of alpha. And this thing here is saying that the y is following a gamma distribution of alpha with beta equal to 1. Do you agree with that? So let's revisit the density function here. Here. So this is the probability density function for the gamma distribution. So what we have is we have a exponential of negative y. And then we introduce a denominator by dividing by 1. So that is essentially introducing a beta equal to 1. And then, so for the denominator, to complete this probability density function, we have a 1 raised to the power of alpha. So that's what we did here. So this is essentially having a beta star equal to 1. And then this thing here, by construction, now equal to 1. This is an integral of a probability density function for all the support. So equal to 1. And let's just complete. We have 1 over beta minus a t, negative 1, and then beta raised to the power of negative alpha. And then we can also group them together, resulting in, so beta over beta is 1, and then beta multiplied by t, okay, raised to the power of negative alpha. And this is the moment generating function for gamma random variable. Okay, so that's that. I think we have 30 minutes, so maybe I should start to introduce material related to homework exercises 6 and 7, which is relating to functions of random variables. Okay, so now let me provide some. So now I'm just going to call property of, I'm not going to write, it's just a property of moment generating function. So for the first one is that if x, y are independent. So now we're talking about two arbitrary random variables. What we did so far is all focusing on one random variables. So now we're talking about two random variables, and then if they are independent, then the moment-generating function for this function of two random variables, so x plus y, I put it in the subscript, and again it's a function of t. So this is equal to the product of the moment-generating function for x only multiplied by the moment-generating function for y only. So this is something that you are going to use a lot for exercise 6 and 7. So one thing to notice is that in the keyword in the homework there are lots of keywords like IID or independent, and this will tells you that you can use this property here. So when you read the questions, make sure you're focusing on those keywords and then identify which of the properties that you can use when you're working on homework. So maybe let me just also provide a proof or a simple elaboration for that of t and then x plus y. So previously you have the expected for e of tx. So now you just consider this x as the sum of x plus y, so that you can rewrite into this way. This is equal to the expected value of etx multiplied by ety. So here just using the exponential rules, like the e of a multiplied by e of b equal to e of a plus b. And then they are independent, and then we can separate the expectation. And this is coming from like the additional material from the video from week 0. That's that. And then by definition, these two are just the moment-generating function for random variable x, and then the moment-generating function for random variable y. And that is this property here. So this is only true when they are independent. So make sure you look for keywords. Without the keywords, you don't want to use this property. Okay. Some more property regarding moment-generating function. Okay. So now for a moment-generating function for a random variable that plus a constant, and this is equal to okay, maybe I can give you the proof to give you the result first. So let's see, using the definition. So e of t multiplied by x plus x plus a. This is equal to the expected value for e raised to the power of at multiplied by e raised to the power of tx. And then the e of at has nothing to do with x, so you can consider that as a constant. And then expected for etx. And then the result is that the moment-generating function for a random variable that shifts by an amount of a constant is equal to EAT multiplied by the moment-generating function of your original random variable x, the moment-generating function. So that is another property. Okay. Then intuitively, it is also meaningful to discuss what is if you scale this random variable by amount of b. What does this equal to? So this is also worth discussing. So now you can see that what we are doing, or many statisticians are doing, is that they are doing some manipulation by applying function to these random variables, and then you want to investigate what is the properties for those resulting or those new functions of random variables. Okay, so again we can use the definition. So e of t multiplied by bx here. And now let me change the order in this way. So e of t multiplied by b, and then group it in the parentheses, and then multiply by x. So now you can consider this t multiplied by b as your new t star. And this will give you the expected value for e raised to the power of t star multiplied by x. And this is also just the definition for the moment-generating function for your random variable x, but the t is now replaced by t star. So now this is a function of t star, not the t anymore. And then you replace the t star by bt again. So this is your third result. So when you scale your random variable by a function, by a constant of a b, you essentially just shift, or you scale the parameter in the moment-generating function, where the moment-generating function is a function of t, and right now it's a function of t multiplied by b. So that's another result. Okay. So now let me group 2 and 3 together to discuss property 4. So moment-generating function of a plus bx. So again, you can use the definition for the expected value, e of t, multiply by a plus bt, bx. Yeah. Okay, so now we can group things accordingly. So e raised to the power of ta multiplied by e raised to the power of bt multiplied by x. Okay, and this will give you, when you bring the constant outside the expected value. So e of, so I use at here. Okay, so you will also have e of at as a constant. And then expected value for e of bt multiplied by x. And this applying, so from here to here, you're using property 2, and then from here to here, you're using property 3. So e of at multiplied by moment-generating function for your original random variable x, but evaluated at function of the parameter b multiplied by t. So this is just a combination for property 2 and 3. And then similarly, you can also have the following. So x plus a over b. A function of t, and then you will have the expected value for t, so e raised to the power of t over b multiplied by x, and then multiplied by e of let's see, A over B multiplied by T. So this is a constant, and then now this is your new T star. So applying 2 and 3 again, you will have E raised to the power of A over B multiplied by T. And that moment generating function for your original random variable x evaluated at T divided by B. So these are all deriving from the property 2 and 3. Okay, I will pause here to see if there's any question regarding these 5 properties here. So some of them can be helpful when you are developing your solution. Any question? Comments? Okay. Can someone remind me if I talk about the moment generating function for exponential distribution or not? Last week, Tuesday. Okay. Then I will. Okay, so then if that is given on Tuesday, then we can talk about this exercise related to 6 and 7, except that this is for normal distribution, this is for gamma. So I'm going to use a different distribution for exponential distribution. For x, I think it's greater than 0, lambda greater than 0. Okay. So now let's suppose x1, x2, and then xn, they are IID. So identically independent, or independent identically distributed following a exponential distribution. So what we want is to find the distribution of x1 plus x2 plus xn. So the sum of a exponential random variables. So this is the similar setting in exercise 6 and 7, except that we are using exponential. So when you're doing the homework, make sure you use the corresponding distribution or the probability density function. Okay. So what we're going to do is to use moment generating function to find the distribution. Okay. So first of all, we want to find the moment generating function for x1 plus x2 plus all the way to xn, and then a function of t. Okay, so let's see, because we have the keyword independent or identically distributed, let's see whether we are able to use, or yeah, so that means we are able to use property 1 because they are independent. So the moment generating function of a sum is equal to the product of the individual moment generating function. So the property 1 is the one that we are going to use. Okay, so now let's rewrite this as the moment generating function for x1 multiplied by the moment generating function for x2, and then multiply by the moment generating function for xn. Okay, so can someone remind me what is the moment generating function for an exponential distribution from Tuesday? Yes. Did I talk about that? Or maybe let me just search for the notes just to see if to double check. Yes, so I give it here. So this is on Tuesday. So this is what I'm referring to, the moment generating function for exponential distribution. Yeah. So now I'm going to copy this term to our solution here for today. Okay, so x1 has the following moment generating function. So 1 minus t over lambda. And then let me use square bracket then. No. So all you need to do is just copying those moment generating function here. Yeah. So that's for x1. But for x2, because they are identically distributed, so x2 also have this moment generating function, raised to the power of -1, and then all the way to 1 minus t over lambda, -1. So what it means is that we have the following: 1 minus t over lambda raised to the power of -n. Does that make sense? Just uncopy of things that have a power of -1. So you have -n as the exponent. Okay, so now by looking at this expression, does this expression reminds you of anything that we go over today? Something we see earlier looks very similar to this. Anything that rings a bell, or? So earlier we see something that looked like this, right? What is this thing that we see today? For gamma distribution, right? So x following a gamma of alpha, beta. But what we have here is a sum of an exponential random variables. So now let's compare these two formulations. So what if I set alpha from the gamma distribution equal to n, and then beta equal to 1 over lambda? Do we have a moment generating function of a gamma distribution from this expression? So what I mean is that if I set alpha equal to n, and then the beta, let me use the other way. Okay, so then let me circle things here. So if I set this alpha equal to n, if I set this beta equal to 1 over lambda, then essentially on the left hand side, or the left part, we have a moment generating function of a gamma random variables that following a gamma distribution with alpha equal to n, and then beta equal to 1 over lambda. So now to answer the question, what is the distribution for a sum of an exponential random variables? The answer is a gamma distribution, and then with this particular parameter. This is your new alpha, this is your new beta. So if you want, you can also call this as like a property or a theorem, a sum of exponential distribution, but they have to be identically independent distributed first, ends up with as a gamma distribution with this two parameter. So that should give you the answer for the question here. What is the distribution of that? Okay, I will pause here to see if there's any question. And also this is related to what we mentioned earlier regarding the uniqueness theorems. So if you can mimic this moment generating function, then you essentially mimicking the distribution. So here we can see that the moment-generating function for a sum of an exponential distribution is mimicking the moment-generating function for a gamma distribution. So then by the uniqueness theorems, we can claim that this new random variable, which is the sum of exponential following the gamma distribution. And this is called the, I think, or at least I call it the uniqueness theorem. So the idea is that, for example, in a normal distribution, although we were going to talk about normal distribution next week. So if you can, so this is the first moment, usually the mean, and then the variance, the second moment is related to the variance, and then the third moment is related like where's the peak, and then also the skewness or something like that. So if you have a moment-generating function that you can describe all the moments for this distribution, you essentially just recover the same distribution. So that is the reason why when you mimicking a moment-generating function, you essentially can say that the new random variable is mimicking the random variable that you already know. So that is the idea of the uniqueness theorems. You are mimicking all the moments, and then you essentially just mimicking exactly the same distribution. So that's the idea. Okay, so let's see. I think this should give you, yeah, so for example, exercise 6, you have independent random variables. And then this is also a sum, but scaled by a coefficient. So make sure, don't forget the k when you're developing the problems. And also here, you have a 1 over n. So don't forget the 1 over n there. So I think the properties and this example should give you enough information for 6 and 7. And we also talk about, also 5 with the properties is done. And also 2 and 3. And yeah, this is just applying formulas. Okay, so I think I'll pause here to see if there's any question. And then I will let me stop recording.